There we go, unmute myself like a good Gen Zer. Thank you, Sarah, and hello, everyone. Before I start, I'd like to acknowledge the traditional custodians of the land of which I'm presenting from today, that is the Bedigal people of the Eora Nation. I pay my respects to the elders, past and present, and extend my acknowledgement to all fellow Indigenous peoples joining us today. My name is Kirsten. I'm a PhD candidate here at UNSW, actually under the supervisorship of Sarah. So today I'll be talking about my PhD project, which is mapping stellar interiors with spectroscopy. Now, there are many ways to map the galaxy for the purposes of galactic archaeology. And the most common way seems to be that, from mentioned a few times during this meeting, is using Gaia astrometry, which is very accurate up to a few kiloparsecs. However, beyond 3 kiloparsecs or so, the uncertainty increases, and there are more precise methods to determine accurate distances beyond 3 kiloparsecs. And one such example is using red clump stars. Now, these are evolved stars that have undergone the helium flash and now fuse helium in their cores. They're distinct features on both the Hertzsprung-Russell and Kiel diagrams, like the one pictured here using Galard DR3 stars. And they have very well-constrained surface features such as temperature, log G, and intrinsic luminosity, which makes them very effective standard candles and have been shown to achieve very high precision distance for estimates up to about 10 kiloparsecs, with uncertainties of around 6%, which is more precise than Gaia at those same distances. So problem solved, right? We get some great standard candles in red clump stars, so we can simply observe a bunch of them and do some really great galactic archaeology, right? Unfortunately, like most science, it's not quite that simple. We have some international super spies in the way of red giant branch stars that are very similar to red clump stars. Now, these stars have very similar stellar parameters in the way of temperature, log G, and iron abundance. And as mentioned, the red clump stars are very effective standard candles. However, these red giant branch stars are imposters and are not. So we need to find a way to effectively and accurately distinguish between these two types of stars. On one hand, asteroseismology is seen as the golden standard to effectively distinguish between red clump and red giant branch stars, which is likely due to red clump stars having these distinctive oscillation behaviors as a result of their characteristic core helium burning. And these asteroseismic parameters, such as the period spacing, effectively distinguish the red clump from the red giant branch, with red clump stars having a characteristic period spacing between 100 and 300 seconds, whereas red giant branch stars are confined to around 50 seconds. And this classification has also been demonstrated using a neural network in Han et al. 2017, which is where this figure is from. Now, this is great. So problem solved again, right? Unfortunately, no. Again, science is not quite that simple. Now, while asteroseismology is fantastic and the gold standard in red clump, red giant branch classification, it is very time intensive, with observation times of days up to years, where the longer observation times expectedly result in greater signal to noise. However, I only have 4 years to do this PhD thing, so we need to find a bit of a quicker way to distinguish between these two types of stars for the purpose of galactic archaeology. Now, fortunately, as it turns out, there is a spectroscopic connection that can be utilized to effectively determine these asteroseismic parameters and therefore distinguish between red clump and red giant branch imposters with less than 2% contamination as well. Now, this figure here is from Hawkins et al. 2018 and shows a comparison between the stacked spectra of 5 red clump stars in red and 5 red giant branch stars in black from the Apogee survey, all with similar surface features, and at which wavelength pixels are most sensitive to this period spacing, which is pictured in the lower panels of this figure. And they found that the period spacing is most sensitive to CN, C, and CO lines, which you can see in the figure. And this method utilized the Cannon algorithm and resulted in a false positive rate of 2% within that classification system. Now, this is promising. However, they do emphasize that further study is required to explore this spectroseismic connection across a broader wavelength range. And that's where my research comes in. So as a first step, we are investigating this spectroseismic connection and apply it to the Cannon in a similar way on 50 X-shooter stars, which is approximately the minimum number of stars required for the Cannon to return a reliable model. So we are currently in the early stages of this analysis. Here we'll attempt to demonstrate that we can detect these spectral differences between the red clump and the red giant branch stars at low resolution, which is about 10,000 for X-shooter stars and X-shooter spectra. And this, what you can see here is just a quick direct comparison, not using the Canon, just stacking some spectra together and just looking at the absolute difference between these two spectra over this similar wavelength range from the Hawkins figure from the last slide. So we do see some little variation here, but we're yet to do some more analysis specifically in the Canon. Now, the second stage of this project will apply this method to 200 stars selected from Galar with K2 and TESS asteroseismology that we have and are in the process of observing with the veleche spectrograph, along with the Anglo-Australian telescope. Now, these 200 are chosen from a selection of those shown in this keel diagram here, with similar temperatures in log G, pending on those pesky clouds. So we've observed about 120 so far, and we're hoping to get some time to observe a further 80. So depending on where those clouds are, hopefully we can get all of them and we can start doing this analysis. Now, the benefit of using veleche is that it has an exceptional resolution, like up to 80,000, and a broader wavelength range between 5,800 and 9,300 angstroms. So this allows us to resolve much more weaker spectroscopic features, such as these carbon-nitrogen lines that you can see in one of our star spectra here. So we can finally also do a bit more of an abundance analysis on these stars. Instead of getting upper limits that you would get from lower resolution spectra, we can start to understand a bit more about the specific nature of how much stuff is in these stars, so to speak. Now, the overarching question here is to find out what is the underlying astrophysical reason for this spectroseismic connection. Now, current thoughts include that the differences in the molecular features may be due to effects of deep mixing along the red giant branch, which makes the red clump stars lower in their carbon to nitrogen ratios compared to their red giant branch counterparts. Or possibly it could be linked to the helium flash stage of evolution. We're still yet to do our analysis and figure out what's going on, but at the end of the day, come back to me in 3 years' time and I might have some answers for you. Thank you all so much.
Nicely done, Kirsten. Thank you very much for that. What questions do folks have for Kirsten? Because I feel like it's, as the supervisor, maybe a bit unfair of me to. Oh, Melissa has a question. Go right ahead, Melissa.
Thanks, Sarah. Thanks. This is really interesting work. Obviously, I'm really interested in it. I had a question about the Galar stars that you're observing with this high resolution spectrograph, which must look gorgeous. Are you observing any time domain? Like, are you observing them more than once, or are you just getting one observation for each star?
So essentially it is one observation for each star, like one night of observation. So currently with the way that veleche works, you get 10-minute exposures. So just multiple of them to get a signal to noise ratio above 50. We've been getting certainly above 50 and near to 100 on the really good nights. So yeah, it's just one observation each time.
Okay, great.
Yeah.
Really high quality. Yep.
Yeah.
Top.
All right, and Keith.
Hello. I was just wondering, how are you selecting that sample of 200? Are you selecting them, for example, to be relatively close by in stellar parameter space? So what was the motivation behind the target selection?
So I will attempt to explain this because Sarah actually did this selection prior to when I started my PhD. But yeah, these stars are very much selected based on similar stellar parameters. So similar in log G, similar in effective temperature. So we can really constrain this connection within those stellar parameters.
Great, thanks.
Yeah, that works as an explanation.
Yes, nailed it.
But because they've already been observed by Galar, we have a decent handle on what those parameters are. So, all right. Any further questions? Melissa, are you back, or is the hand still up?
Sorry, that's just me not knowing. I'm just going to lower that. Yeah.
Okay. I thought maybe you came up with another thing. All right. Simon Campbell, what did you want to say?
Great, thanks for the nice talk, Kirsten. I'm just wondering if lithium's in your spectral range.
Probably, and considering it's been raised as quite the problem this week, it would be interesting to see how abundances work. So another further step on this research is not just to use the Canon for spectral features like effective temperature, log G, and ion abundance, but also extend it to further abundances, which has been demonstrated to be effective. Like you can include or raise and make bigger words are not working anymore, but you can increase the label space using the cannon to multiple abundances. So it's kind of like a in 2 years time sort of thing.
Yeah. Thank you.
I mean, I would point out we have Galal lithium abundances for the stars that are lithium rich enough that they're above our detection limit for these stars.
But the veleche data will be much better, so you'll get
Yeah,
lower that floor for lithium.
absolutely.
Interesting.
Yeah.